Hi everybody. Today I want to take a look at chapter 2, problem number 25. The average atomic mass of some elements may vary, depending upon the sources of their ores. Naturally occurring boron consists of two isotopes with accurately known masses. Boron 10 has a mass of 10.0129 AMU, and boron 11, which has a mass of 11.003931 AMU. The actual atomic mass of boron can vary from 10.807 to 10.819, depending on whether the mineral source is from Turkey or the United States. Calculate the percent abundances leading to the two values of the average atomic masses of boron from these two countries. Now, I already covered the one that was from Turkey in the PDF that I sent out to you guys. I'd like to take a look at the one that's from the United States this time. So we're going to be getting an average atomic mass of 10.819 AMU. Okay, so this is a weighted average problem, and the first thing I want to do is go over averages and weighted averages just for the little refresher. So, averages. We get some measurements. They're going to be represented here as x1, x2, x3, and I've written an ellipse here to indicate that this could just go on and on. We could have as many measurements as we want, okay? In order to calculate that average, all right, which I've written here as x bar, we're going to add all of our measurements together, on and on for as many as we have, and then we're going to divide by the number of measurements that we have, okay? If we want to like picture this, basically what this average is it's going to be a value that's going to be roughly in the middle of all of our different points, okay? Now, what that assumes, though, is that each one of these points is equally likely, okay? When that's not true, what we can do is the weighted average, okay? So what we're going to do here is we're going to have data, x1, x2, x3, on, and each one of these is going to have different weights, okay? If you want to picture a scenario where this is true, this is how, for instance, I calculate your guys' grades, right? The exams are worth so much percentage, the quizzes are worth so much percentage, and I add up all of the different points that you got, and I multiply them by their various weights, and then I take an average to calculate your final grade, okay? So, what we're going to do with the weighted average is we're going to multiply each by its weight, each data point by its weight, like I said. We're going to add them all together, and then we're going to divide by the sum of all the weights. Okay? Now, in our problems that we're dealing with right now, we have a special case. All right? This is when all of the weights sum to 1. Okay, so that means that A plus B plus C here, this is all going to add to 1. This whole fraction reduces down to just this having the weights times their data points added together. Okay, so let's go back to our problem here. The first thing that we can do is set up the weighted average that is going to get us to our 10.819 value, all right, with the things that we don't know and the things that we do know, okay? So what don't we know? What we don't know are the abundances. So I'm going to have x1 be one of the abundances, and I'm going to have x2 be the other abundance, okay? So let's go ahead and take these values of the naturally occurring isotopes and multiply them by their abundances, which are going to be our weights in this case, okay? So we're going to have 10.0129 AMU times x1 plus 11.00931 AMU times x2, and that's going to equal our value of 10.819 AMU, which they did not feel a need to put a unit on in the problem, but we certainly are, because that's just good practice. Okay? So when you first look at this, you say, well, I've got two things that I need to know. How could I possibly solve for one of them? This is the classic two unknowns, two equations problems, okay? So we basically don't have enough information to solve this right now. What we need is another equation, okay? So what we're going to do is we're going to use the fact that we know that these abundances, x1 plus x2, is going to equal 1. Remember, that was our special case for these kind of problems, okay? And we're going to take that equation and we're going to solve now for one of the values. We'll solve for x1, okay? So x1 is going to equal 1 minus x2. All right. Now I'm going to take that value and I'm going to substitute it in for x1 up here. Okay. And what I'm going to get is 10.0129 AMU times 1 minus x2 plus 11.00931 AMU times x2 equals 10.819 AMU. Okay. Now I only have one unknown, and this is essentially just algebra to get the final solution. First thing I need to do is distribute this through. So I'm going to have 1 times this value and negative x2 times this value. So I'll get 10.0129 AMU minus 10.0129 AMU times x2 plus this term here, 11.00931 AMU times x2. That is all going to equal, oops, I ran out of room, but let's write it down. 10.819 AMU. Okay. Now I need to gather my like terms together. I want all of the values that are times x2 to stay on the left-hand side of the equation, and I want to move this guy over to this side of the equation over here. Okay. And remember that I have to keep my signs with my values there. So when I simplify this, what I'm going to get is I'm going to choose to take this one here first, the positive 11.00931 AMU minus the 10.0129 AMU times x2 And that is going to equal, got this guy over here, 10.819 AMU minus that value right there, 10.0129. Okay, now I'm going to divide by this coefficient right here over to here, and I can get a value for x2. So x2 is going to equal, this would be my numerator here, 10.819 AMU minus 10.0129 AMU divided by 11.00931 AMU minus 10.0129 AMU. Okay. Now I'm going to need to get out the calculator. We'll adjust the camera just a tad bit there. Okay. And what we're going to do is we're going to start off with the parentheses. We're going to do 10.819 minus 10.0129, close that parentheses. We'll do our division symbol. Open a parenthesis, 11.00931 minus 10.0129, close that parentheses, and we get our value of 0.809004325, right? So if we take a look at this, though, this has 5 significant figures. This has 6 significant figures. So we're going to be limited to 5 significant figures. So our answer that we're going to take here is going to be 0.80900. Okay. The next digit that we had here was a 4, so we round down in this case. All right. Now, we've solved for x2, but we still need to get x1. Now, we could go back and do the exact same procedure to get to x1, but we can be way more clever about it than that. Okay, we can go back to this equation that says that x1 is equal to 1 minus x2. All right. So in this case, x1 is going to equal 1 minus 0.80900, which is going to equal what? 0.1. Let's get our calculator out again. 1 minus 0.80900 9 1, and we will take the 2 zeros at the end to give us the same number of significant figures, because this one value here is one of those constants that has as many significant figures as we need it to have. Okay. Now, if we want to represent these in percentages, we can take x1 times 100% and write that as 19.100%. And we can take x2 times 100%. And that is going to be 80.900%. And that's it. We've managed to figure out our abundances.